Hello everyone. I'm going to work on your test 4 review for you. Your test 4 can be found on the Hawks Learning website. You're going to have all the same values that I have if you go in and work the review. But I suggest doing that. Maybe watch me do this and then try it, or try it first and then watch me do it. Your real test 4, you have 2 chances. Highest grade will be kept, and use this video to help you out on your test. I'm going to try to explain each problem as best as I can. So let's get started. Alright, some of the values that I put in, I've already done the calculations, but I'll tell you how I get them. So on this problem, this is a uniform distribution problem because it says it's distributed uniformly between 5 and 10 inches. So between 5 and 10 inches, that's 5 inches, right? So if you said 10 minus 5, you'd have 5 inches. So this tells you that trees are going to grow between 5 and 10 inches, and the probability of them growing any of that is the same between 5 and 10 inches. So we want to know, what is the probability that a randomly selected cedar tree will grow less than 6 inches in a year? So less than 6 inches. All right, so if we have, think about the number line. I guess that would kind of make sense here. So we had 5, 6, 7, 8, 9, and 10. And we want to know the probability of less than 6. So that would be the probability that the tree is going to grow either 6 or less, and it's at least going to grow 5 inches. We know that. So since there are 5 units between here and here, the probability of less than 6 is just going to be one of those units over the 5. So that's your answer, 1/5 or 0.2. All right. Now so all this given information indicate on the curve where the given x value would be. So we're just going to the x value. Go to 27. So you just move this over until you get to 27. There it is. The diagram below is an illustration of the empirical rule. Remember that? That was from a few sections back. Select the missing label for the diagram. All right, the empirical rule is always symmetrical. So if this is mu minus 2 times the standard deviation, this has to be, this is mu minus 2 times the standard deviation, this has to be mu plus 2 times the standard deviation because of symmetry. All right. Now, what value of z divides the standard normal distribution so that half the area is on one side and half is on the other? Round your answer to 2 decimal places. All right, so half on one side and half on the other. Well, here's the standard normal distribution. Remember, the area under the entire curve is 1. So we'd have 0.5 here and 0.5 here if you look at right here in the middle. Well, what z is that right there in the middle? That's z equals 0. If you wanted to get technical, I guess, and round to 2 places, that would be 0.00. To me, 0 or 0.00 would be the same, so that's what we need to put in. If you want to see that in the table, I can show you. So if I just look at the normal table, see right here, 0.00, 0.5. So that would be 0.5 on the left is what that means, because that's the way the tables read. So if there's 0.5 on the left, there has to be 0.5 on the right. All right. So that's it. Find the value of z such that 0.04 of the area lies to the left of z. All right, it's important that you understand exactly what the problem is talking about. 0.04 of the area is to the left. So this is problem number 5. So if we're under the curve here, we want to figure out the z value where 0.04, so right there, 0.04 would be to the left of that z value. All right, so we need to look in our table And remember, the z's to the left of the center are negative. So we need to look in our table and get as close as we can to 0.04 as an area. We're not looking up 0.04 as a z-score. We're trying to get as close as we can to 0.04 as an area and see which z-score that corresponds to. So as close as we can get is this number right here, 0.0401. That's 1/10,000th away. You can see this other one is close, it's 8/10,000ths away, but this one is closer to 0.04. So what z-score would that be? Negative 1.7, let's see what we are here, 5. Negative 1.75. When I clicked on it, it put the answer in the blank for me. Alright, the diameters of ball bearings are distributed normally. The mean diameter is 149 millimeters and the variance is 36. Find the probability that the diameter of the selected bearing is greater than 141 millimeters and round your answer to 4 decimal places. Alright. So first, you want to write down all of the given information. We were told that the mean was 149. We were also told that the variance was equal to 36. And we want to know the probability that if you randomly select a bearing that its diameter is going to be greater than, that's important, 141. Alright, so for this problem we need the z-score because we're trying to figure out a probability from all of this given information. And our formula for our z-score is x minus mu over sigma. So that is x is that 141 minus the mean 149 over sigma. Now sigma is the standard deviation. We weren't given the standard deviation, we were given the variance. So we need to take the square root of 36. We get 6 as the standard deviation. So we don't use the variance in any formulas. So anytime you're given a variance, just know you have to find the standard deviation by taking the square root of it. Alright, so when you work this out, all z-scores will round to 2 places. So if you say 141 minus 149 and divide by 6, then you're going to get negative 4/3 or negative 1.3 repeating. But we're going to stop here at the second number because that's as far as we take a z-score out, and that would be rounded to that position. Right? So what about the greater than? Well, greater than tells me, if I look at my standard normal curve, I know that my negative z-score is going to be somewhere over here on the left. I'm just going to guess. I'm going to say it's going to be about right here. Well, the greater than right here, that tells me that I want to find the area to the right. Greater than will always be the area to the right and less than will be to the left. The way that our table reads is it always gives us the area to the left. So what I need to do, if I look up this z-score, it's not going to tell me this area here. It's going to tell me this area here. So what I need to do to find this other area is say 1 minus the area that it gives me. And that'll tell me the shaded area that I have there. So I want to go to the z-score, and I'm looking up a negative, so I'm going to go negative infinity to negative z. And then I wanted to look up negative 1.33. So negative 1 point, and this is the 3 column right here. So negative 1.33. So that value there, that's what I want to subtract from 1 because it was a greater than problem. So I'm going to say 1 minus 0.0918. Now if you plug that in your calculator, you're going to get 0.9082. And that's what I'm going to put in. Alright, problem number 7 is very similar to problem number 6. It gives us a mean wait time. Now, it doesn't give us a variance. It gives us a standard deviation. So we don't have to find the standard deviation it's given. And we want to find the probability that a person will wait more than, that's important, more than 6 minutes. So very, very similar to this problem. It's just the numbers are going to be changed because it's a greater than problem. So we were given the mean equals 7 and standard deviation equals 1. We're looking for the probability that x is greater than 6. So we're going to use the same z-score formula. It's going to be 6 minus 7 divided by 1. Now, of course, we know 6 minus 7 is negative 1. Divided by 1 is still negative 1. But we need to remember it's 0.00. Now, since it's a greater than problem, we're going to say 1 minus the area that we get when we look up a z-score of negative 1.00. So I'm going to look in the negative z-score chart. I'm going to look up, let's see, here's the 0 column here, the 0 in the hundredths. So negative 1.00. That's 0.1587. So I want to say 1 minus 0.1587. And when I do that, I get 0.8413. And that's my answer. Cool. Alright, so these are real easy to figure out because it says select a scenario which is an example of voluntary sampling, and then it gives you 4 choices. So voluntary, you just read through these choices and say which one of these do you think the people in the scenario are volunteering to do. It will be this last one right here because it says the store sends out an email asking you to participate in the online surveys. I'm sure everybody's gotten those emails about online surveys. Those are voluntary. Of course, most of the time when I get them, I don't do them. So, you know, that's the only one that's a voluntary survey. You can read through the other ones. And this one right here says which is an example of a simple random sampling. Read through all the choices. You can look here at the last one. Company management wants to determine the average amount of time that employees are late. They do this by randomly picking a list of employees and record their arrival times on a particular day. So it's a simple random sample. All right, that's the last one there. Okay, now starting with number 10, this problem is a little different than 6 and 7. Read through the problem and you'll be able to tell a little bit of difference. We still get a mean here. We have a variance, so we'll have to find the standard deviation. It says if the claim is true, what is the probability that the mean monitored life would be greater than, that's important, and this 81.8 months, that's our x, but here's the different part, in a sample of 89 monitors. So we're not talking about one monitor, we're talking about if we took 89 monitors, what would the probability be that their monitor life would be greater than 81.3 months? Alright, so that changes our formula just a little bit for our z-score. Not a lot, just a little. So this is called the central limit theorem. And it says if we're taking a sample of items and we want to know a probability, then the way we get our z-score is x minus mu over sigma divided by the square root of n. So that's going to be the sample size. All right, so we were given that the mean was equal to 83. We were given that we wanted to know the probability that x was greater than 81.3. We were also given the variance, which we don't need the variance, we need the standard deviation, but we were told the variance is 100, so that means the standard deviation is 10. Okay, so we have everything for our formula except for this n, and we were told there were 89 monitors. Okay, so we're going to plug everything in, and it was a greater than, right? It was a greater than problem, so we're going to say 1 minus the area we get after we plug everything in. So I get 81.3 minus 83 all over 10 divided by the square root of 89. It's important that you use your calculator until, correctly so that you can get the right answer, of course. If you use your calculator correctly and you round this to 2 places, you should get negative 1.60. So I would plug that in your calculator and make sure that you get that. The way that I do it, the easiest way, is to find the difference here. And then since you have a fraction on the bottom, you would flip and multiply. So take the difference, flip this, say it times the square root of 89, and then divide that by 10. And you'll get the negative 1.60 when you round it to 2 places. All right, so again, this was a greater than problem, so we're going to say 1 minus. We look up this area in our z-score chart. Remember, it was a negative, so we need the... Now, notice the tables aren't given. Where are they at? Oh, no, don't worry. Here they are right here. Tables. standard normal table, and we had a negative z-score, so we're going to look at the area negative infinity to negative z, and we're looking up negative 1.60, so negative 1.6, and then the O is in the last column, negative 1.60. So we're going to say 1 minus that, and that will give us our probability. So 1 minus 0.0548. When you plug that in your calculator, you should get 0.9452. So that's the answer. All right. This problem is very similar to that problem. You can see that the mean diameter is given, a standard deviation is given. Now here's n, here's our random sample. N is going to be 31, and we want to know the probability the sample mean will be greater than 132.2. All right, so it's another greater than problem. We've done a lot of greater than problems. There's going to be some less than problems in a minute, but all of these have been greater than problems. So this is problem number 11. So that was 11. We were told in the problem the mean was 131, the standard deviation was 7. We were told that they took a sample of 31 of these things, and we want to know the probability that x is greater than 132.2. So we simply plug all of this in our z-score formula. So our x is 132.2 minus our mean is 131 over our standard deviation divided by the square root of n. So 7 over the square root of 31. When you plug that in your calculator and you round to 2 places, you should get 0.95. So let me remind you again with a picture what we're actually doing. I didn't draw a picture on the last few. So we're under this is the standard normal curve. A z-score of 0.95 is going to be, that's almost 1 standard deviation. So it's going to be to the right, and we're trying to figure out the probability greater than. All right, so we're figuring that out. So to do that, we look up our z-score and we say 1 minus, because when we look this z-score up, it gives us all of this area. I don't know how much it is, but I know it's bigger than 0.5. It's probably going to be about 0.6 or 0.7. We'll see in just a second. So we're going to say 1 minus, because it's a greater than problem. So let's go to our table. Go to tables, standard normal, and now it's negative infinity to z. And we want to look up 0.95. There's 0.95. So we're going to say, it was more than I thought. It's 0.8. We're going to say 1 minus 0.8289. All right, do that in your calculator, and you should get, let's see, how about I'll do that one out. 1 minus 0.8289, 0.1711. All right. So moving on to number 12. All right, so we're given a mean life of a computer is 84 months with a variance of 100. Again, anytime we have the variance, I'd go ahead and find the standard deviation. All right, if he is correct, what is the probability that the mean of a sample of 99 computers would be less than, our first less than problem, hooray, is less than 86.8 months. All right. So let's write down everything that we have. We're given that the mean life of a computer is 84 months, and we're told the variance is 100. Again, we don't use the variance in our formulas, so standard deviation is the square root of that, so it's 10. We're told that we have a sample of 99 computers, and we want to know the probability that the mean life will be less than 86.8. All right, So we need our z-score, and it's a less than, so we're actually just going to take the value that's given in the table. I like that one. It's one less step to do. So we have x minus mu over sigma divided by the square root of n. Whenever you do all of that, you should get about 2.79. So I bet you this number that we look at is going to be really small. Because if we are 2.79 standard deviations to the right, then the area that we find in the chart is going to be, well, if we take the, I'm sorry, I said it's going to be really small, but this is a less than problem. So if we take the value from the table, because it's less than, it's going to be really big. So it's going to be a big probability. I say a big probability. It's probably going to be 0.8, 0.9, 0.95, somewhere around that. Let's see. So let's look that up. Standard normal. So remember, we're going to take the value from the table. 2.79 as a z-score. 2.7. Look, it's even more than I thought. 2.79, that's 0.9974. So, well, let me just put that answer in, 0.9974. I think I can just click on it. Maybe not, we'll see. Nope, I have to put it in, 0.9974. So what that actually means is there's a 99.74% chance that the computer's, the 99 computer's life would be less than 86.8 months, which kind of makes sense. If you figure out, or you think that it's 84, what's the probability that 99 is going to be less than 86.8? Pretty good chance. All right. So moving on, problem number 13. This problem shifts gears a little bit. The reason why this is different is because we're no longer talking about means, we're talking about proportions. So when we start talking about proportions, we have different formulas. Okay. So it says, suppose 57% of politicians are lawyers. If a random sample of 564 is selected, what is the probability, or what is the proportion of politicians who are lawyers will be less than 51%. The probability that the proportion of politicians, man, that's a tongue twister, who are lawyers will be less than 51%. Round your answer to 4 decimal places. So again, we are given proportions instead of means, so our formulas have to change. All right, so we're told 57%. That's our point estimate. That's what we think. That's what they said they think, right? And we are told that we have a sample size of 564, and we want to know the probability that the actual is less than 0.51. All right, so we need to figure out the z-score, and it's a less than problem, but again, this has changed a lot. Now, notice we weren't given the standard deviation. We have to figure that out. And there's a formula we have to use to figure it out. And the z-score formula is no longer going to be x minus mu, because we don't have a x or a mu. We do have a p. It's going to be p minus p hat all over sigma sub p hat. We put this little symbol here to remind us that we're finding the standard deviation of our proportion, and it has its own formula. So the way that you find the standard deviation of a proportion is you take the square root of p hat times 1 minus p hat all over n. So most of the time these are going to be decimals, and then you're going to have to divide and get a really small decimal, and then you're going to take the square root. All right, so be very careful when you plug all of this in. I would probably do the numerator, then I would divide by n. If you have to, write that number down and then take the square root of it, or figure out an easy way to do it in your calculator. All right, so I've already plugged all of these numbers in. I'll write them down just so you can see what I'm doing. So it's 0.57, that's p hat, times 1 minus p hat. So that will be 1 minus 0.57, well that's 0.43. And then we were given a sample size of 564. So if you do all of that in the calculator, now, this is where you should make sure that you don't round this too far. When I say too far, so let's look at our final answer. We want our final answer rounded to 4 places. So if I want to round a final answer to 4 places, I want to make sure that the numbers that I'm going to use to get to that answer are taken out more than 4 places. So what I did, usually as just a safety measure, I would say if you need your final answer in 4 places, put your intermediate values, that's the values we're using to get there, I would take them out to maybe 2 or 3 more places. I know 6 places or 7 places is a pain, but I would do that to be safe. So whenever I did that in my calculator, I got 0.020846. So I took it out 6 places. Okay? And so these are the values that I want to plug into my z-score formula. So I'm going to say z is equal to 0.51 minus 0.57 over 0.020846. Now when I plug that in, remember, if you get out 10 or you get out -20 or something like that when you find a z-score, you know you messed up. All of your z-scores are going to be usually between -3.5 and 3.5. They're not going to be much smaller or bigger than that. So when you plug that in and you round to 2 places, you get -2.88. All right, remember, this is a less than problem. So what that means is, if I look this value up in my table, I'm going to take the value that it gives me as my answer, as my probability. So I need to go to my table, go to Tables, Standard Normal, negative infinity to negative z. And then I want to look up -2.88 right there. I think you can actually copy this if you want. Look at that. I'm going to copy it. And since it's a less than problem, I'll just put it right here. I'll paste it right here. That's my answer. That's rounded to 4 places already. Okay, this is another problem. It's exactly the same as far as you work it out, the way you work it out. You have a percentage, you have a sample size, and then you want to know the probability that it will be less than 10%. So that means it's another less than problem. All right, I'm going to speed through this one. So we were given our point estimate, or they think is 12%. Sample size is 55.6. We're looking for the probability that the proportion is less than 10%, so that's 0.10. So our z-score is going to be, well, before we can find our z-score, we have to find our sigma sub p hat. That is our standard deviation of our proportion, and that's the square root of p times 1 minus p divided by n. So our p hat, was 0.12, and if you subtract that from 1, that's 0.88, and then that's divided by 556. When you do that in your calculator, you should get about 0.013781. All right, and if I plug this in my formula now, it's 0.10 minus 0.12 divided by 0.013781. If you round that to 2 places, you're going to get -1.45. All right, so it's a less than problem. So I just want to take the value from the table. So let's go to my table, negative infinity to negative z, and I want to look up -1.45. All right, so that is my probability. There is a 0.0735 chance. That's 7.35%. So that's pretty small. And that's what I'm going to put right here. All right, I don't see any percentages anymore. So we must have moved on to a new type of problem. All right, let's see what it says. At a local college, the study found that students earned an average of 14.3 credit hours per semester. A sample of 123 students was taken. What is the best point estimate for the average number of credit hours per semester for all students at the local college? So we're looking for the best estimation of hours. The only thing that we're given about hours is that the 14.3. So that is our point estimate. That's what we have to use, because that's the only information we have when we're talking about the average number of credit hours. Okay, in a sample of 77 curtains, the average length was found to be 36.4 inches with a variance of 2.7. Give a good point estimate for the population standard deviation. Here's the variance. It's 2.7. So if we want the population standard deviation, we take the square root. That's all we have to go on is that 2.7. All right, so I will say the square root of 2.7, and that will be my answer. All right, and it says to round to 2 places. Now, when I was looking at this problem earlier, when I was looking at some of the answers, the answer that was listed was 1.6. Now, if you put in the right answer on this problem and it counts it off because the program rounds to 1 place, but the problem says to round to 2, then just send me an email and I'll give you those points. It's not a big deal, okay? Or if it does it to everybody's, which I'll look and see. If it does, I'll just add a couple points to everybody's. Anyway, I'm going to put in 2 decimals like it says. So that would be 1.64. Let me double check and make sure that I put in the right answer. So we're given a variance. We want to find a standard deviation. I'm going to do it one more time. 2.7 square root. All right. So 1.64 is what I'm going to put in. I like those problems. They don't take very much work. All right. This is another point estimate problem. It says the sample variance is 39.1. Okay, what is the best point estimate for the standard deviation if the variance is 39.1? So I need to take 39.1, that's the variance, take the square root of that. All right. So it says round to 1 place on this one, right? So it would be just 6.3. If I rounded to 1 place, 6.3. All right, what is the best point estimate for the population's variance if the sample variance is 39.1? Well, I mean 39.3. If all we have to go on is that 39.3 as a sample variance, and we want an estimate for the population, well then we just have to use that estimate for the population. So if we have a sample variance and we want an estimate for the population variance, we just have to use what we're given. All right. A sample of 15 buttons is randomly selected and the following diameters are measured in inches. Give a point estimate for the population standard deviation. Uh-oh. Population standard deviation. Do you remember how to do that? There's a good chance that that has passed you by, but this is a good time to practice. What I would do is either use a calculator or use Excel or a website to get the population standard deviation. So you just copy the data. I'm going to open up Excel. I'll show you how to use that. Excel is so powerful. You can use it to do all kinds of things. Anyway, all right, so I'm going to copy the data in here. So there's all the data. And then I'm going to find the standard deviation. So you don't see standard deviation over here. You got to go to more functions. All right, and there's standard deviation. And so let's see if it gives it to us. We're going to actually have to, let me go back. I want to make sure that I think it's overwritten something that I put in there. So I'm going to delete it out. You can delete, I'll delete this whole thing out. Anytime I'm unsure, I'll just repaste that, yeah, because I don't want to mess it up. All right, I'm going to put my cursor here this time, and I'm going to go over here, and I'm going to go to more functions, standard deviation. And now I think it wants me to put all these values here to here. That's what I want. So I'm going to select all those values now. And let's see what it does. Look, it gave it to me. So you actually have to go in and select the values to get it to work out. Now if you do it out by hand, it's going to take a while. If you do it in a calculator, it doesn't take very long. Once you figure out Excel and you get it to do what you need it to do, it's pretty quick. So I didn't see how many decimal places it wanted us to round to. It says to 3 decimal places. So if I round that to 3 decimal places, I believe that was 0.061 because it was like an 07 there on the end. All right. Now this one says, consider the value t such that 0.05 of the area under the curve is to the right of t. Select the graph. All right. Well, this area is to the right of t that's shaded. Now this is to the left of t. This is on both sides of t, and this is between t. So the only one that was to the right of t, like it asked, is the first one here. So it's that one. Just select that graph. Now consider the value, okay, blah, blah, blah. Okay, assuming the degrees of freedom equals 3. All right, so here's 0.05 here, because it says the area 0.05. Degrees of freedom 3 is right here, so you just select that one. That's the answer. That's not a trick problem. All right. Now, on this problem, we are wanting to first calculate the sample mean. Well, I'm just going to copy the data and go back to Excel. So I'm going to put this in right here, and I'm going to find the mean of that set of data. So, average. So there's the average, or the mean. All right. So that was step 1. It says to round to 1 decimal place. So that would be 18.7. Calculate the sample standard deviation. Well, I'm not going to do that out by hand. I'm going to come over here. And let's see, I'll just select right here. That's where I want to put it. I want to go in and do standard deviation. I just have to tell it which of these I want to do that for. And that will be those. Okay, and it gave it to me right there. So my standard deviation is this number. Let's go back. And it says round the standard deviation to 1 place. All right, so that's 5.2. Now I'm definitely, if I have to use these values like the mean and the standard deviation, I'm not going to use 5.2 if I have to use them in a formula. I'm going to want to go back and get those out to a few decimal places. Find the critical value. So the critical value for an 80% confidence interval. You can find a table in your book that lists these critical values. I can show you how to find the critical t. This is a t test too, by the way, because you're given a sample of values. So it's a t distribution. So I'll show you how to do that real quick. For 80%, let's go to here. So this is problem number 21. So we have 80% confidence interval. The critical t value is t sub alpha over 2. That's a sub alpha over 2. So alpha for 80%, that's going to be 1 minus 0.8 or 0.2. All right, so and the way you get that, you say the 0.8 comes from the 80%. All right, so that's alpha. So it's going to be t sub 0.2 divided by 2. And so that's t sub 0.1. It's really 0.10, but I mean 0.10 is the same thing. All right, so to find the critical value, we're going to have to go to the table. You see tables. Now it's not the standard normal table, it's the t table. In one tail is what we're looking at. So we go to the column that had the 0.1. All right. So we got our 0.1 here. That's the column that we go to. Also, we need to know what the n was equal to. All right, so I may have to, here, let me get out of this. That's 1, 2, 3, 4, 5, 6. The way you find degrees of freedom is you say n minus 1. Okay, so we don't use 6, we use n minus 1 would be 5. So 0.10 down to 5. All right, there is our critical value, 1.476. I'm going to copy that. 3 places, that's how it is. All right, on part 4, step 4, this is where we're going to construct our confidence interval. Now, we need to be careful with this formula. I think when I first wrote it down, I didn't put the square root of n down here. I just left that out, and that does affect your answer if you don't have that there. So we've already found the mean. We found the critical value we found the standard deviation, and we have to put the square root of n down here. So again, I'm kind of crazy when it comes, if I know that I have to round, I hate plugging in answers that are rounded, so I'm not going to plug in that 18.7 or whatever I put in earlier. So 18.6667 plus or minus, all right, now our critical value, 1.476, times the standard deviation. Now, earlier I put in 5.2. I'm not going to put that in. I'm going to put it in what it was in Excel, carried out to a couple of places. All right, and then that is going to be all divided by the square root of n. Now, n is the number of items that I had. Remember, degrees of freedom was n minus 1, so it was 5. Well, n was 6, because I had 6 scores. All right, so I'm going to divide that by the square root of 6. Now, do this math, add and subtract it, and you should get, when you round, your lower endpoint is going to be 15.6, and your upper endpoint is going to be 21.8. All right, those are your two answers that you should get. So in problem number 22, this looks like it's very similar. Of course, it only has 2 steps. So, as we look at this, let's see. We have 27 water samples for mercury concentration. So it looks like n equals 27. This tells us the mercury concentration with a standard deviation of 0.0074. Determine the 90% confidence interval for the population mean mercury concentration. Assume the population is approximately normal. All right, so our sample size was 27, so our degrees of freedom is going to be 26. Also, we have a 90% confidence interval. So that would be T sub alpha over 2. 90%, 1 minus 0.9 is 0.1, so 0.1 divided by 2 is 0.05. And then we were told that n equaled 27. That was the sample size, so our degrees of freedom is 26. So let's go to our tables so we can find our critical value. All right, so we're at 0.05 in one tail. Our degrees of freedom is 26. So that means our critical value is 1.706. Now actually construct the confidence interval. So we're going to have to figure out all those. Well, it gave us a lot of the values that we need in the problem. Like it gave us the concentration, the mean concentration was 0.097. It gave us the sample standard deviation was 0.0074. So, and we just found the critical value. So it's the mean plus or minus the critical value times the sample standard deviation. All right, when we plug this in the calculator and work it out, to save time, I've already plugged it in. You get 0.095 as your lower bound and 0.099 as your upper bound. And so your lower endpoint is the first one, your upper endpoint is the second one. So the lower endpoint, of course, would always be smaller. All right. Number 23. It looks like we have proportion here. So, of course, that makes our formulas change a little bit. Let's see what it's asking. NASA is conducting an experiment to find out the fraction of people who black out at G-forces greater than 6. In an earlier study, the population proportion was estimated to be 0.38. How large a sample size will be required in order to estimate the fraction of people who black out at 6 or more Gs at 98% confidence level with an error of at most 0.03? So this is a lot different because it's asking for a sample size. We have formulas for sample sizes depending on whether we have a mean or a proportion or whatever information is given. So on this problem, since we have proportions, our formula for sample size is going to be z sub alpha over 2, that's our critical z-score, squared, times p hat times 1 minus p hat over the error squared. Okay? And so if it gives us the error, that's good. If it doesn't, we have to figure it out. I believe it gave us all of the values that we need. The only thing it didn't tell you, it said a 98% confidence interval, but for a 98% confidence interval, our critical value for 98%, you can find this in tables, is 2.33. We were told that our point estimate was 0.38, and we were told that the error was 0.03. So we just plug all of this stuff in. So it's going to be 2.33 squared times 0.38 times 1 minus 0.38 is 0.62, right? Divided by 0.03 squared. All right, now when you plug all of that in, you are going to get a decimal, but pay attention. You can't have 0.165 of a person. So since you can't, you always round that up. It doesn't matter if that's 5 or greater, the decimal. If you have a decimal, you always round it up. So that'll be 1422. That's our answer. All right. The FBI wants to determine the effectiveness of their 10 most wanted list. To do so, they need to figure out the fraction of people who appear on the list that are actually caught. Since we have a sample of 554 criminals drawn and 232 were captured. So we want to estimate the proportion of people who were caught. So that would be 232 out of 554. So we can do that in a calculator. You say 232 divided by 554, and you'll get a decimal. When you round that to 3 places, it's 0.419. Now on to, let's see, on to step 2 of this problem. So now they want us to actually construct the 95% confidence interval for this population proportion. All right, so we're going to need that proportion that we had, that 0.419. I'm not going to use that. I'm going to carry it out a couple of places. Okay, so this is 24. We had n equals 554, x equals 232, and we figured out in step 1 that p hat was equal to 0.4, it's 1877, but we had to round that to 3 places. Okay, so in step 2, this is where we want to do our confidence interval. 95% confidence interval. All right, and so for a 95% confidence interval, this is the z sub alpha over 2, the critical z-score is 1.96. All right. And the way that I construct this confidence interval is I say p hat plus or minus e, the margin of error. Now the problem did not give me the margin of error, so I have to figure that out. That's the main thing that I have to figure out before I can proceed in step 2. The margin of error is equal to the critical z-score times the square root of p hat times 1 minus p hat divided by n. Okay, and I know what my critical z-score is for a 95% confidence interval. It's 1.96 times the square root of, all right, I'm going to substitute that in. I'm going to plug that in and go out to 5 places there, and then I have to put 1 minus p hat. So you do that in the calculator. Let's do that real quick. So 1 minus 0.41877, 0.58123. And that's all over n. That's the sample size of 554. All right, so whenever you multiply that out, you need to multiply that, divide, take the square root, and then once you get that answer, you say it times 1.96, and you should get around 0.04108. That's our margin of error. So we're going to take our point estimate, and we're going to add and subtract 0.04108. And that's how we get our two endpoints. All right, so whenever you add and subtract that, you get 0.37792 and 0.46008. And let's see what it wants us to round to. It says to round to 3 decimal places. So the lower end, I'm going to get 0.378 if I round that to 3 decimal places. And on the upper end point, I'm going to get 0.460. Moving on to the last question. Number 25. It says, first, step 1, suppose 1,350 floppy disks are drawn. Of these disks, 67 were defective. Using the data, estimate the proportion of disks which are defective. Enter your answer as a fraction or decimal number rounded to 3 decimal places. Okay. All right, so we're trying to figure out, this is number 25. We were given that n was equal to 1,350, and the number of defective floppy disks was 67. So our proportion is going to be 67 over 1,350. And when you do that in a calculator, you get about 0.0496293, and so on and so forth. Let's see what it wants us to round this to. It says to round to 3 places. Okay, so I'm going to round to 3 places. So that is, all right, so if I round to 3 places, that's rounding that 9. So that's going to go up to 0. So it's 0.050 when you round to 3 places. Now they want us to actually construct the confidence interval. All right, so this is a little different. 85% confidence interval, that's not something that you see a lot. So that was step 1. Step 2, 85%. So you have to figure out the z-score for that. So the alpha is actually 0.15. So the critical z is going to be z sub 0.15 divided by 2, or z sub 0.075. All right, so what you have to do is, if you have a weird percentage like that, so there's going to be a positive value and a negative value, a positive z and a negative z, such that 0.075 of the area is on each side. If you look up this area in the chart, it will give you the negative answer, but we're actually just going to use the positive answer. Because of where we plug it into our formula, we want the positive answer. So if you look that up, you're going to get the z-score is equal to 1.44, so that's the critical z value. So over here it'd be negative 1.44, over here it'd be positive 1.44. But the way that the formula works, you'd want to plug in the positive value. And I can show you why when we get to that point. All right, so our formula is p hat plus or minus e. All right, so we have p hat, right? That was our 0.0496293 plus or minus. Well, I have to do the margin of error. That's the big step here, and a big part of step 2. And that's where I use my formula that I used on the previous problem on 24. The critical z value times the square root of p hat. So that was 0.0496293. I'm getting kind of, carrying it out that many places is taking it a little too far, so it would probably be okay if we didn't take it that far. But I also have to plug in that other number, so 1 minus 0.0496963. So that's 0.950 3037. All right, so I'm going to multiply those together. Then I'm going to divide by 350. Then I'm going to take the square root of that. And after I do all of that, then I'm going to say it times 144. And that's going to give me my margin of error. And you're going to get somewhere around 0.00854. And so that's what I'm going to add and subtract. Since I'm adding and subtracting it, I'm going back to why I chose the positive z. If I would have put a negative z right here, my error would just be a minus. Well, if I was to add and subtract a minus, that's the same thing as adding and subtracting a plus, since I'm a positive number, since I'm doing the same thing. So that's why it really doesn't matter if you use the positive or the negative of the critical z value, but in general, we always just use the positive because we like positive numbers better than we do negative numbers. All right. So once I do that, I'll have my two endpoints. So when I add and subtract that, I'm going to get those two endpoints and I'm going to round them. And when I do that, my lower endpoint is going to round to 0.041 and my upper endpoint is going to round to 0.059. All right, and that finishes your review. All right, so let's see what it says we got wrong. It's probably the way that I entered in some stuff. So I want to review. And I'm going to go and see. So it says I got this one wrong. All right. And it looks like it didn't save my answer when I put it in. So make sure that, and let's see, let's double check. 0.05, assuming the degrees of freedom equals 3. So 0.05 and 3. So it looks like I clicked on the wrong thing. So for this one, I clicked on this. For 0.1, it clearly says 0.05. So make sure that you click on the right value. All right, even I make mistakes. And then number 7, it looks like I may have just pushed the wrong keys whenever I punched this in. The answer was 0.8413 and I put 0.8143. So I'm pretty sure we got the answer was right, I just put it in wrong. So what I would do is, as you work these out, make sure that you keep your answers, go back in and check and make sure everything's put in correctly. I probably just sped through this a little too fast, but everything else was correct. Thank you for watching the video. If you have any questions, make sure you send me any emails that you may have about any problems, homework, anything like that. Have a great day.